This conference will now be recorded.
Hello everyone. The topics for today's discussion: conjugate acid-base pair, though it is already started in the last class, but we will continue this. Conjugate acid-base pair, Lewis theory, that is the third theory which is left. Two theories we have covered. Limitations of this theory, then strong acid versus weak acid, strength of acid, and if time permits, strength of bases and strong base versus weak base. Fine. So conjugate acid-base pair, we already have seen, that is the primary idea that we already know. So here, suppose in general, if I write any acid HA, after dissociation, we will get H plus and A minus. So this A minus is basically conjugate base. Okay, conjugate base of HA. Now in this case, here is the stability of this conjugate base. So stability of conjugate base when increases, that means acidity of HA that will increase. So this species stable means what? The equilibrium will be easily shifted from left to right. So we will have H plus more and more. And that means HA is very strong acid. So that is why we are getting more and more of H plus, and A minus is very stable. So this species is stable, which is found in the right hand side. Now in this table, as you can see, here some acids are mentioned in the left hand side and the corresponding conjugate bases that are mentioned on the right hand side. So HCl, Cl minus, then H2SO4, just remove one H, you will get the corresponding conjugate base, which is HSO4 minus. Similarly, we have H3O plus. So if you consider it as if it is acid and you are removing one hydrogen, you will get the neutral species H2O. So H2O is the conjugate base of H3O plus. And if you consider directly H2 as acid, then after removal of one H, you are now left with HO minus. So that is why HO minus is the conjugate base. Then take organic molecule, methane, CH4. Though we know it is not acid, but suppose if you consider it as acid and you are removing one H, we are getting this species CH3 minus. So this is the conjugate base. Now as I have said that stability of conjugate base, when it is increasing, that means acidity is decreasing. So the reverse statement will also be true. That is when stability of conjugate base is decreasing, then acidity of HA that will also decrease. So here you can easily understand this. So I will take two extreme. One extreme we have HCl. So the corresponding conjugate base is Cl minus, and the last, that is if you see, it is 100% ionized in water. Then in the middle part, whatever examples you are seeing here, they are actually in between. So they are not very strong, they are not very weak. They are intermediate, that is weak. But if you consider these three species, H2, HO minus, CH4, they are actually, you cannot call them acid at all. So they are at the last extreme. So acid strength is increasing as we are moving up, and as we are moving down, it is strong zone, this is the weak zone, and this is the negligible zone. Now from negligible zone, if I am taking this example of CH4 minus, the corresponding conjugate base is CH3, negative charge over carbon, right? Now HCl, we know its acidity compared to methane, obviously it is high. So that means the stability of Cl minus, that will also be high than the CH3 minus ion. So this is the reason. Now if you look at the right hand side, here this zone is negligible. That means these bases are very stable because these bases are generated from acid which is very strong. So obviously the bases will be very stable. Now when it is stable bases, that means what? That means they will not show very good basic property. So that is why here it is mentioned it is negligible basic property. Now if we go to the middle zone acids are weak acids. So the corresponding conjugate bases like SO4 2 minus, F minus, HS minus, all this will be not very stable, not very unstable, something in between. So basic strength is gradually increasing as we are moving down. So these are very stable, they are non-reactive, that means their basicity is almost nil, negligible. Then in the middle zone, the basicity is intermediate type. And now if you move in this position, now 100% protonated in H2O. So the tendency to be protonated, remember in the last theory, second theory, what we have seen, Bronsted, that is a tendency to be protonated, that is a tendency to accept H plus. That is the definition of base. So in these three cases, as it is very, very unstable, so its chance of capturing H plus, that is very high. So after capturing H plus, it will be converted to CH4, which is very stable. So in this case, the acid part, there is, you can also say from reverse direction that the conjugate acid of CH3 minus anion is methane, or you can say the conjugate base of CH4 is CH3 minus. So both statements are fine, right? So the point is only one H will be missing if you want to recognize any acid, conjugate acid base pair. So in this case, in this table, as we are moving in the left hand side, as we are moving down, the acidity is gradually becoming less and less. But if you moving down in the right hand side, basically the basic strength is becoming very, very high. So this is the relationship between conjugate acid and acid base pairs. So why this discussion is important? Because if you are getting any problem where 3 to 4 species are given and you have to find the order of acidity or order of basicity, you can consider the corresponding conjugate acid or conjugate base and then see if they are stable or not. That is depending on the stability order of the corresponding conjugate acid or base. You can now determine what is the acidity order of the or the basicity order of the actual species that are given in the problem. Okay, so this is the significance of this discussion. Now we have the last theory, which is Lewis theory of acid and bases. So Lewis proposed a more generalized concept. So as you have seen, when we have moved from Arrhenius to Bronsted, it is comparatively more generalized. And when you are moving from Bronsted to Lewis, again it is becoming more generalized. So more generalized concept we are getting, more generalized theory we are getting. That means now it will cover different types of species and acid and bases. And that is the reason limitations will be less. But it is also true when you cover many species and acid and bases, some another type of limitations can also arise. But we'll come to that point later. First see what Lewis theory actually states. So this is the most general among these three concepts, and in which Lewis considered an electron pair to define a species as an acid or base. So in this case, our definition of acid and base, that will be based on electron pair. Until now we have talked about H plus or HO minus. In case of Arrhenius, we have talked about H plus, that is any species which can give H plus, that is acid. Any species which can give HO minus, that is base. Then in Bronsted we have seen acid is proton donor and base is proton acceptor. And in the third theory, now we are talking about the definition of acid and bases on the basis of electron pair. So whether a species, it will be able to capture electron pair or it will be able to donate electron pair, based on that now we will define acid or base. So according to this concept, an acid is a species. Now it may be molecule, that is neutral molecule, or it may be carrying some charge. Any species that accept electron pair, while base is, that is acid will accept electron pair and base will donate electron pair. Okay, or in other words we can say a substance which is vacant orbital to accept one or more pairs of electron, that can act as Lewis acid, because as it is accepting electron, so there must be vacant orbital, otherwise how it will accept? The electron will reside somewhere after acceptance. So that is why vacant orbital Its presence is important. And a base is consequent to any substance with unshared pair of electrons. So there must be unshared pair of electrons. Then only it can donate this electron pair. Fine. A Lewis acid is a positive ion or an electron deficient molecule. Now, in this definition, as Lewis acid is something which is accepting electron pair, that means there must be some deficiency. Otherwise, why it will accept electron? So deficiency must be there, or it may be any positive ion, because positive ion means there is positive charge, so there is lack of negative charge, so they can accept. Similarly, when it is Lewis acid, you will see mostly it is neutral molecule, but it is containing some lone pair. So suppose any neutral molecule, there is presence of nitrogen or oxygen with lone pair, so it can behave as Lewis base, or it may be anion also carrying some negative charge, right? Now, in coordination compounds, the ligands acts as Lewis base and the central metal atom or ion that accepts a pair of electron from the ligand. Now, this ligand is behaving as Lewis base and the metal is behaving as Lewis acid. So, as this theory, that is Lewis theory, it is very general theory, the most general. So now coordination compounds can also be covered in this theory. So for example, if we have any cation, suppose nickel H2O whole 6, and nickel is having oxidation state 2. Now water is neutral molecule, so it will not satisfy this oxidation state. So outside we will place the charge 2+. So in this case, nickel 2+ cation that is actually surrounded by different water molecules. Okay, so these water molecules, they are basically donating electron pair towards this nickel. So there is lone pair present over oxygen, so total 6 H2O molecules, lone pair over oxygen, that can be donated to nickel 2+. So these water molecules, they are behaving as Lewis base, right? And this nickel 2+, which is accepting electron pair from these ligands H2O, they will be treated as Lewis acid. So coordination compounds, that is not all the compounds, there is also exceptions. In some cases, we can say that here the metal ion, metal atom or ion, because sometimes the metal may be neutral also. So for example, NiCl4. So in this case, NiCl4, suppose here the charge is 2 and total 4 chlorine we have taken, and there is negative charge will be 2 negative charge will be extra, and that can be satisfied by any other anion which is present outside this coordination sphere. Okay, actually this example I cannot take. It may be any neutral molecule also. So suppose I am writing here any metal M which is already having a 0 charge, and with it there is some ligands presence, that is L6. So this metal may be carrying some positive charge 2+, 3+, or it may be 0 also. And here ligands L, I have written here L in general, and M which is the metal. So this metal may be neutral, that is a central metal atom or ion, both may be the case. So in this way, some compounds in coordination chemistry, we can say that the ligands are behaving as Lewis base and central metal atom or ion, as it is accepting electron pair from these ligands, so they will behave as Lewis acid. So this is Lewis theory of acid and bases. Some examples we will see, because this is the most general among these 3 theories. So obviously now the examples that you are going to see, you will find them very versatile. So until now, examples of acid and bases mostly we have seen where H is present, or in the base there is presence of HO minus ion. But here you will not, that requirement is not mandatory here. So see, here we have examples. For Lewis acid, first, electron deficient molecules such as BF3LCl3 BeF2. Remember, in the limitations of Bronsted theory, in the last class, we have seen that this type of molecules, you cannot call them acid if you considering Bronsted theory, because according to Bronsted theory, acid should give H plus. But in this molecule, where is H? There is no H. So we should not call them acid according to according to Bronsted, also Arrhenius basically. But when you consider Lewis theory, this molecule can also be treated as electron deficient acid. Why? Because it is electron deficient, and as it is electron deficient, electron pair can be accepted by them. Now, why it is electron deficient? Boron. It is having total 3 fluorine attached to it. Now, boron is from group 13, that is the first member. Group 13, general electronic configuration is NS2, NP1. Now, boron is from second period, so its general configuration is 2s2, 2p1. That means outermost total number of electron 2 plus 1, total valence electron is 3. Basically, if you do not want to go into the details, group 13 means the last digit that will be denoting the number of valence electrons. So these 3 valence electron boron will be using for bond formation with fluorine. So from fluorine also, fluorine will use 1 electron for bond formation with it. So all the electrons of boron, which is denoted by this red dot, all are used up. And surrounding boron, how many total electrons are there? 2, 2, 2, because total 3 bonds, that means total 3 electron pair, to total 6 electrons. So 6 electron means its octet is not complete, and as octet is not complete, it will try to accept 2 more electrons so that it can fulfill its octet. So this is the reason why it is electron deficient. Same explanation you can also put for AlCl3, because aluminium, that is also from group 13, the same problem is also there. What about BeF2? In BeF2 we have 2 beryllium fluorine bond. Beryllium is from group 2. It has only 2 electrons, and both the electrons used up for bond formation with fluorine, and the electron from that are coming from fluorine, I am writing it with cross sign. So that means surrounding Be, total 4 electrons are there, which is also not fulfilling octet. So these examples are electron deficient molecules, and it can accept electron pair, and that is the reason, according to Lewis theory, you can call them acid. That is Lewis acid, not Bronsted acid or Arrhenius acid. Second example, all metal ions like this. So these metal ions, they can form coordination compound. Remember, in the previous slide I have mentioned Ml6. Outside there may be charge or not, depending on ligand is anionic ligand or neutral ligand. Metal is carrying some positive charge or not. So just take chromium 3 plus. So if it is chromium 3 plus, there is 3 positive charge. And if ligand is anionic, so these ligands, as it is carrying negative charge, it can donate to this chromium 3 plus electron pair. And if it is carrying some negative charge also, so L may be water. So in this case, it is neutral, and it will donate electron pair, this lone pair over oxygen, that will be donated to metal. Or ligand may be like Cl minus or Cn minus. So in this case, negative charge density, that will be donated. So here Lewis base, that is a corresponding Lewis base, it may be neutral or it may be anionic also, but we are here discussing Lewis acid example. So metal ions like this, they can also form coordination compounds. So they are now behaving as Lewis acid because they are carrying positive charge. Third example, molecules that contain polar double bond. Polar double bond that are present in this type of molecule. So polar double bond means the one of the bond of this double bond, it can be broken, and there will be positive charge over one atom, negative charge over other. So if you take simple example of carbon dioxide. So here we have polar double bond. Why we are calling it polar? Because the double bond is present between carbon and oxygen, and oxygen is very electronegative compared to carbon. So if you are breaking any of these bond, positive charge will be over carbon and negative charge that will be over this oxygen. So in this case also, because of this type of polarization, you can generate positive charge over carbon And that is what is mentioned in the third point, that molecules that are carrying some polar double bond, it should be polar, otherwise this type of charge separation will not be possible. So here I have fully broken the bond, but it may be partial also. Partial means then I will write it partial, that is del sign is used when you want to mention partial charge. So it is not fully developed positive charge or negative charge, and the bond is not fully broken, so I am writing it with dotted sign. So here also this carbon center, it can behave as Lewis acid. Similar explanation you can also apply for SO2 sulfur dioxide, SO3 sulfur trioxide. So sulfur is less electronegative compared to oxygen, so that is why polarization is possible. Next example, molecules in which central atom can expand its octet due to availability of empty d orbital. Fine. Here, if you look at this molecule SiF4, now carbon is from group 14. Now the next element is silicon. Now in carbon, there is no d orbital present, and it is from second period. Now silicon is from third period, and in third period silicon will have vacant 3d orbital. Now because of this vacant 3d orbital in SiF4 molecule, there are total 4 silicon fluorine bond. So silicon is its electronic configuration. Remember, for carbon it is 2s2 2p2, so it will be 3s2 3p2. So total 4 electrons are there. All these 4 electrons will be used up for bond formation with 4 fluorine. But remember, there is also presence of 3d. It is true there is no electron in 3d, but 3d is available. It is vacant and it is available. So that is why, because of this available vacant d orbital, it can also accept electron pair for some from some Lewis base, obviously, which can donate electron pair. So same explanation you can also use for SF4 or FeCl3. Then the last example, carbocation. So in general, I can write it as R3C plus. Now this R may be H, this R may be any alkyl group. So in this case, we have 3 methyl group surrounding it. Now carbon, it is carrying positive charge, and carbon, its valence electron 2s2 2p2, and it will use all these 4 electrons for bond formation. But here, as positive charge is there, you cannot consider 4 electrons. There are basically 3 electrons. It is using for 3 bond with 3 CC bond basically, and another electron will come from the other carbon. But if you count total number of carbons surrounding it, it is basically 6 electrons. So here also octet is not complete. So that is the reason carbocation can also behave as Lewis acid. So these are all examples of Lewis acid. Next we will see examples of Lewis base. So Lewis acid electron pair acceptor, but Lewis base, it will be the reverse. That is, it will now donate electron pair. So a Lewis acid, if it is showing acidic behavior, so obviously there must be presence of a Lewis acid also. Lewis bases also. Molecules with one or more lone pair of electrons that will behave as Lewis base. So in this case, we have lone pair over nitrogen, water lone pair over oxygen, alcohol lone pair over oxygen. Then we have ROR, which is basically ether. Here also lone pair over oxygen, and amine, that is RNH2. So these molecules, they are neutral molecule, and there is heteroatom containing lone pair, and this lone pair can be donated. So that is what is Lewis acid. Then all anions. So here you can see all these species, they are carrying some negative charge, F minus, Cl minus, HCl minus. So this negative charge can also be the source of electron pair, which can be donated to Lewis acid. Then the third example, molecules that contain carbon-carbon multiple bond. such as ethylene. Here we have two examples, that is any CC double bond, not just ethylene. It may be any other alkyl group also both sides, or triple bond. So here in this molecule, if you take this example, there is one sigma bond and one pi. Now pi bond can easily be broken, and the electrons that are present in pi bond, that can be donated to some Lewis acid. Okay, so this pi electron density, that can also behave as Lewis base. Though it is true that if you compare with the first two examples where actual negative charge or lone pair is present, so compared to this, which are more available, so compared to this, if you consider this pi electron density, obviously it is not so Lewis basic type, that is Lewis basic nature is not so high like the first two examples, but still it can behave as Lewis base. But remember, compared to first two examples, this third example, this is not so significant, but still there is a chance. Then all metal oxides such as CaO, MgO, Na2O, they can also behave like this. So here, as they are anionic type of nature, so they will remain as cation and anion. And anion means there is negative charge or oxygen. That can also behave as Lewis base. But it is not very important example. The most important example Lewis base is the first two, not the 4 and 3 and 4. But the last one, that is also another very good example, CH3 minus. So CH3 minus, it is carrying negative charge over carbon. So again, it is basic. You can also consider them in this second point. But second point examples are basically inorganic species. And CH3 minus, though this is anion, but here it is example from organic chemistry, so that is why it is mentioned separately. But that is also type of anion. You can consider them in the second point also. So these are the examples of Lewis bases and Lewis acids, right? Limitations. It is true that this is the most general, and if you are thinking that's most general, so it will not have any limitation, but that is not the case. Because what happens when you are making any theory from narrow, it is becoming more broader and broader. There are some other type of disadvantage also gradually generated, right? So though it is more general compared to Bronsted and Arrhenius, but several drawbacks are also present. Because now the drawbacks that you will see, it is not like the limitations that you have seen in the first two theories. Now the drawbacks are different types of drawbacks, because it is covering many different variety of species. So when it is something is covering variety of species, so it is becoming so general that sometimes it cannot explain acidity or basicity behavior. So this gives general idea and includes all the coordination compounds. Remember the first slide of Lewis theory, we have seen that coordination compounds, this is a good example for Lewis base, Lewis acid simultaneously present, but it is not applicable for all the organic or coordination compounds. Coordination compounds, there is a separate chapter in class 12. So when you will read it in detail, you will see that all the coordination compounds, you cannot explain them on that. It is not that all the metal ions are behaving as Lewis acid, or all the ligands associated with them, they are behaving as Lewis base. No, that may not be always true. Because formation of coordination compounds, it is actually slow process. But when we talk about acid base neutralization reaction, this is a fast process. So this is one type of drawback which we cannot explain on the basis of Lewis concept. Lewis concept does not explain the behavior of well-known protonic acid like HCl, H2SO4, HNO3. So why we cannot explain them as on the basis of Lewis theory? Because Lewis theory is all about electron pair acceptance. But when you talk about HCl, HNO3, H2SO4, they are basically donating H bases. So you can explain them better with Arrhenius or Bronsted, but not Lewis. So that is the problem. And it doesn't form coordination bonds with bases. So HCl, that if you add any Lewis base to it, you will not get any type of electron donation from Lewis base. that you expect between one Lewis acid and one Lewis base. That type of reaction you will not expect between these two. So it doesn't form coordination bond with bases. Coordination bond means try to understand the difference between covalent bond and coordination bond. So suppose we have a bond between A and B, and here if it is purely covalent, one electron is coming from A, another electron is coming from B. But when I am saying that it is coordination bond, or sometimes it is also called coordinate covalent bond. Now what will happen? This is also, it will look same, but here both the electrons are coming from one atom. Once it is donated by B, now it is shared between two. That is, once it is donated by B, now it will behave as if it is a covalent bond, just like the previous example. But here both are coming from same atom. Similarly, when we have reaction between Lewis acid and Lewis base will donate electron through lone pair or negative charge. So the bond that you will get between La and Lb, that is basically coordination bond, which is also written sometimes like this. Arrow marking is there so that you can understand from which side to which side the electron is donated. Okay. So this type of coordinate bond we cannot explain between a Lewis base and a protonic type of acid, HClHNO3. So therefore, according to this theory, we cannot be regarded as acids. Relative strength of acid and bases are not explained by Lewis. Remember, in conjugate acid-base theory, you can compare acidity and basicity depending on the conjugate base that you are getting from the protonic acid, whether it is stable or not. So we have taken two examples. Remember, from HCl we get Cl minus conjugate base. From CH4 that example I have used, you are getting CH3 minus. So in this case, you can compare the corresponding conjugate base, its stability. So here Cl minus is very stable, so that is the reason HCl is very acidic compared to methane. So you can compare that HCl is more acidic than CH4. But this type of comparison, that is the relative strength, when 3 to 4 species will be given, how you will compare that which is most Lewis acidic, that type of explanation, it can be given, but several experiments will be required. It will not be so easy like this that we have done in case of conjugate acid base pair. So relative strength of acid and bases we cannot explain in this theory. Fine. So now we will discuss problem. Whatever we have learned, that is 3 theories, right? Here we have total 4 species. HCO3 minus, which is bicarbonate anion, then hydronium ion, then we have bisulfate ion, HSO4 minus. So this type of anion you can get from H2SO4. And we have HSO3A. So among these 4 species, we have to compare the acid strength order. Acidity you have to check. Now, we know that if you know the conjugate base, corresponding conjugate base of any acid given, when you are trying to predict stability order, first thing that we have to do, the corresponding conjugate base we will write. So from the first species, the corresponding conjugate base, you are getting CO3 2 negative charge. From the second one, you are getting the corresponding conjugate base, which is neutral water molecule. From the third one, you are getting, after removal of H, you are getting SO4 minus. And from the fourth one, you are getting SO3 F minus, right? Now, how to know which one is most stable? Now, CO3, if you write it, the full structure, the negative charge is like this. For water, there is resonance is not possible because it is already neutral molecule. For SO4, total 4 oxygen, 2 negative charge like this. And from the last species, SO3F. Basically here 1 oxygen that will be with hydrogen, and that hydrogen is basically removed. So this is SO3F. So in these examples, only one neutral molecule will have, which is water. Rest of them are negative charge. Now the negative charge, they can undergo resonance. So when there is resonance, the negative charge is delocalized. So higher is the resonance, higher will be the delocalization, and stability will increase with increasing delocalization. Now, neutral molecule, obviously you have to give preference. That means this should be more stable. But remember, if resonance is very, very high, it can even outweigh this neutral molecule stability. So here H2O is the only neutral molecule among these four conjugate bases, but still SO3F minus, it is very, very resonance stabilized. And the reason is here fluorine is electronegative. So when negative charge will take part in resonance. So another resonance structure I can draw. Now the negative charge is here, double bond is here, this double bond is not disturbed, and F. So this type of negative charge, it is coming towards S, and it will be easier because of this presence of electronegative atom. Here also it is possible, and you will get now negative charge here. But remember, it will not be as you are seeing in the last case. So in the last case, resonance will be maximum. Fine. And here also in case of carbonate, resonance is possible. So here maximum stability that you will get from 4. And after 4, the next stability you will get from water. So it will come, that is the, I'm talking about stability of conjugate base. That order I am talking about. So 4 will be more. Then after 4 it is 2. Then we are left with 3 and 1. Now in 3 and 1, in case of sulfate, the resonance amount is high because here negative charge is delocalized, total 4 oxygen atoms. But here it is over 3 oxygen atoms. So obviously delocalization is high. So after 2, it should be 3, and then we have the last one, which is 1. So this is the stability or order of conjugate base. But remember, we have to find correct sequence of acid strength order. But acid strength order is same as stability order of conjugate base. So that is why 4231, that will also be the acidity order of these 4 species. So correct option, option D. Here also it is 4, 2, 3 and 1. Fine. Which of the following fluoro compounds, all are fluoro compounds, right, is most likely to behave as a Lewis base? The previous problem is based on conjugate acid base theory, right, which is basically we have seen in Bronsted theory. Now the question is Lewis acid base theory. So we have some fluoro compounds BF3, PF3, CF4, SiF4. So which one most likely to behave Lewis base? That means in which case the lone pair donating tendency is maximum. Now lone pair donating tendency maximum, obviously lone pair should be present, otherwise how it will behave as Lewis base or negative charge. But all these 4 are neutral, they are not carrying negative charge. So you have to explain it on the basis of lone pair availability. Boron, which is from group 13, and it has total 3 valence electrons, and all the electrons are used up in bond formation with 3 fluorine. It is basically electron deficient species, and BF3, no question of Lewis base, but it is actually Lewis acid. So obviously it is not correct answer. Then we have PF3. Now phosphorus is from group 15, total valence electron 5. Total valence electron 5 means 3 will be used up for bond formation with 3 fluorine, and 2 will be extra, which will be basically lone pair. So there is a chance of showing Lewis basicity. But we will also see the other 2. Carbon, silicon, both are from group 14. That means total 4 valence electron, the last digit of the group. Total 4 valence electrons, and here I will write, see, formulas are same. So a same type of explanation. So 4 CF bonds, all 4 electrons used up, there is no electron deficiency, and also there is no extra electron. So they are not Lewis acid, they are not Lewis base. So most likely to behave as Lewis base, that will be option B, group 15, not 13 or 14, because of presence of lone pair. Next question, which of the following is Lewis acid? pH3. Remember in PF3 what we have seen, that 3 electrons will be used up for bond formation with 3 hydrogen. 2 electron extra. So why it will behave as Lewis acid? It has no electron deficiency. Then we have BMe3. Now not just BMe3, any boron compound with 3 bonds. I am writing it in general because it will also applicable for any other alkyl group. 3 electrons used up. Here our groups are CH3, but it may be H also, F also. Explanation same. So 3 electrons used up and there is electron deficiency. Octet is not complete. Total number of electrons, if you consider all the electrons involved in the 3 bonds, total electrons 6. So this should be the correct answer. But why these two not? NaH, this is basically ionic compound, that is Na plus and H minus. So though it is positive charge, but you cannot say that it is Lewis acid, because here after removal of this electron, sodium is attaining the noble gas configuration of neon. Sodium is having configuration neon, which is atomic number 10. After that it is 3s1. Total 10 electrons here, 1 electron here. Atomic number of sodium 11. So when this 1 electron is lost, now it has reached neon. So you cannot say there is electron deficiency. It is actually stable species. So it is not electron deficient. And the last one is NF3. Nitrogen is from group 15. That is same type of explanation that you have used for pH3. So for nitrogen, total 5 valence electron, 3, that is 2s2 2p3, 3 will be used up for bond formation and 2 electron will be extra, and that is why it is not Lewis acid. So BMe3 is the correct option. Okay. Three reactions are there, and all these reactions, there is involvement of this species H2PO4 minus. It is asking that 3 reactions that are given involving H2PO4 minus anion, in which of the above reactions this species acts as an acid. Options C, 2 only, 1 and 2. That means first reaction only, second reaction only, or it may be first and second reaction. It may be third reaction only, sorry, it will be 1, or it may be the first reaction only. Okay. So you just have to recognize in these 3 reactions which one is acid and which one is behaving as base. So H3PO4, it is giving a proton to H2O, because H2O is accepting proton from H3PO4, right? So H3PO4 is giving proton towards it and itself is becoming H2PO4 minus. So water is accepting proton, that means it is behaving as base, and this is the corresponding conjugate acid. Now H3PO4, as it is giving proton, so it is behaving as acid, and this is the corresponding conjugate base of this. So here H2PO4 is not behaving as acid, right? Then the second example, H2PO4, it is giving proton towards water, itself is converted to HPO4 2 negative charge. So this is the conjugate base and this is the acid. This is base and H2O is accepting proton. So this is the corresponding conjugate acid of H2O. So here you can say H2PO4 minus is behaving as acid. And the last example, H2PO4 minus, it is accepting proton from H. It is converted to now O2 minus. And as it has accepted proton, it will behave as base. This is the corresponding conjugate acid. And it is donating H. So this is acid. This is corresponding conjugate base. So here it is mentioned acid 1, base 2. That is, here I have written acid and conjugate base. You can also write it like this. That is acid 1 because it is the acid in the left hand side, and in the right hand side H3O plus is the conjugate acid of water. So that is why it is mentioned acid 2. So it is also behaving as acid but in the reverse direction. So acid 1, base 2, acid 2, base 1. So here it is behaving as base. In the last one also it is behaving as base. Only in second one it is behaving as acid. That is true. Fine. So correct option should be option A. Only the second reaction. This is a problem which is a little different. Ammonia released on quantitative reaction of 0.6 gram urea, formula given, with sodium hydroxide. So there is some reaction going on between urea and sodium hydroxide, and ammonia is one of the product of them. So first you have to write the reaction between urea, NH2CO NH2, and NaOH. The balanced equation you have to write. Why balanced equation important? Because you have to understand from 1 mole of urea how many moles of ammonia you are getting, and that is the reason why you need balanced equation. So this is the reaction. One urea molecule, it is written in this way, and see here 2 NaOH is taking part. So as if this CO part and ONA together is making Na2CO3, and from this side you are getting one ammonia, and this side you are getting another ammonia. So this is basically 1 mole urea reacting with 2 moles of NaOH. It is producing 2 moles of ammonia. So from 1 mole ammonia, 1 mole urea, you are getting 2 moles ammonia. So this is the most important thing that you have to do, the first step. Next is, here amount is given, but you need molar mass, which you can get from this formula. Now this is CH4N2O. So from this formula you can calculate molar mass of urea. So 1 carbon 12, 4 hydrogen, 2 nitrogen 14 into 2, that means it is 28, and 1 oxygen 60. So if you add, you will get 60. So this is the molar mass of urea. If it is molar mass of urea, number of moles of urea present in the given mass 0.6, that is equal to 0.01, that is the number of moles. Now we know 1 mole urea requires 2 moles ammonia. So when it is 0.01 moles of urea, you will get 0.02 moles of ammonia. Now to neutralize this ammonia, which ammonia is basic? This is basic. So you need some acid solution. Now it is asking which of this acid solution will be able to neutralize, right? Quantitative reaction. That means it will be exactly neutralized. So when it is 0.02 moles of ammonia and the reaction between ammonia and HCl, it is basically 1:1 reaction. It will produce NH4Cl. That means when it is 0.02 moles of ammonia, it also requires 0.02 moles of HCl. Now here it is given in terms of normality and molarity for HCl, it is same. Now when you multiply the volume and the corresponding molarity, then you get the number of millimoles. So from 1, if I multiply it 200 into 0.4, even I will say that full calculation you don't have to do. 0.02 moles of HCl required. In terms of millimole, it is basically just divided by 1000. So it will be 0.02 into 10 to the power minus 3, right? So in which case after multiplication you will get this 0.02 into 10 to the power minus 3. This value you should get after multiplication. If you multiply 200 and 0.4, don't waste that is your time in the full calculation. That is not required. 2 and 4 is there, so it will be something involving 8. So this cannot be correct option. Then the second option, 2 and 2. So it will give you something related to 4. So this is also not correct option because we just need 2. Then the last one will be also involving something 1. Only these three, 100 ml and 0.2. So 100 ml and 0.2. Sorry, it is not multiply. It is not division, it is multiplication, because from moles we are moving to millimoles. We are decreasing the unit. So obviously it will be multiplication. Multiplication means it is 20 millimole. Sorry for the mistake, it is 20 millimole. So 20 millimole, if you multiply these two, 100 into 0.2, you will get 20 millimole. So this should be the correct. Okay. So from the first one, basically you will get 80 millimole. From the second one, you will get 40. Last one, you will get 10 millimole, right? So obviously, these are not giving you 5. So you don't have to do full calculation. Just looking at the options, you can directly understand which option is correct. So first step in this problem, you have to write the balanced equation between ammonia and NaOH, so that you can understand how many moles of ammonia you are getting from 1 mole of urea. That is the first step. This information is important. Once you know this, the second step is you have to find the molar mass of urea, because given mass of urea, you have to convert it to moles, and for that you need molar mass. So given mass divided by molar mass, now you are getting the number of moles. Once you know the number of moles of urea, just double it, you will get the number of moles of ammonia. Next step is ammonia, how it is reacting with HCl. It is 1:1. That means the number of moles of ammonia to balance it 0.02, exact number of HCl required. Now concentration is given in normality, but for HCl normality molarity same. Just multiply the volume given in ml and the strength in molarity. If you multiply, you will get the value in millimole. So 0.02 moles means when you convert to millimole, it will be multiplied by 10 to the power 3. So it is basically 20 millimole, and only from third option you can get 20 millimole. Okay. So today we'll end here, and some new topic will be started. So I will not start today. Thank you for listening.